Now, an equation that you will see a lot when you go into the water relations literature, especially at the stand level, is the Penman-Monteith equation. This has been around a while. It's older than me, which means it's really old. But this is an equation that was formulated to express the combined effects of the environment and vegetation on transpiration from a stand of vegetation. This type of approach to understanding the controls over transpiration is sometimes called a big leaf approach, because this type of equation aggregates the complexity of, for instance, a stand of vegetation into just a few numbers, like canopy conductance that we'll talk about in a second. But it aggregates the complexity of ecosystems into one or two numbers, and it's very useful. But it also subsumes a lot of complexity, and we always need to keep that in mind. So this equation could be a little intimidating to look at, but it's actually relatively straightforward. There's really only a few components. So there's a couple of components that express the effects of the environment or weather. And I'll put those in black. So there's D, and that's vapor pressure deficit. That's a measure of the dryness of the air. So, and then the other is net radiation. Okay, so those are the two main environmental factors in this equation. There's two main vegetation factors. And that's GC, which is canopy conductance. I'll talk about that in a minute, but it's roughly equivalent to the crown conductance that I talked about when I talked about the whole tree level, but it's got a little bit more complexity in it. And then GA, that's the boundary layer or aerodynamic conductance. So the A just means aerodynamic conductance. All the other terms are constants or weakly temperature dependent. Okay? So the Penman-Monteith equation is used in a lot of ways. You could theoretically use the Penman-Monteith equation to predict the transpiration rate of a stand or to indirectly measure the transpiration rate of a stand by measuring, for instance, canopy conductance, measuring the parallel sum of all leaves in the canopy. But if you just think about that for a minute, that's tough to do. And actually, there's a citation in your notes. The Milne et al. Paper actually talked about what would be necessary to do that. And in that Sitka spruce canopy they were working in, they said you need like about 150 measurements of individual leaf stomatal conductance to parameterize that GC term for one point in time. So in reality, that is seldom done. Now, sometimes the Penman-Monteith is used to predict transpiration, but we use a model of GC, for instance. like a process model of GC or an empirical model of GC. We seldom measure GC directly. Now, on the next slide, I'll talk about another use of the Penman-Monteith that's also used a lot, that's pretty powerful. And that other use is to invert the Penman-Monteith equation. So this formulation here is just the inverted Penman-Monteith equation. And by inverted, I mean it is solved for GC. So do the algebra to move GC to the left side of the equation. Okay, now here you have a situation where if you measure transpiration, which is E, lambda E, GA, which is aerodynamic conductance, which is often calculated as a function of wind speed. If you measure transpiration, aerodynamic conductance, and then net radiation and vapor pressure deficit, which we generally measure with meteorological instruments. If you measure those things, you can then calculate canopy conductance. And just like at the tree level where I said crown conductance is a really powerful physiological measure, the same is true of canopy conductance. But it's more complicated. So if all that was in your measurement of transpiration was just tree transpiration, then that inverted GC, that GC term, would just be the stand level equivalent of crown conductance. It would be the parallel sum of conductance of all the leaves in that ecosystem. Now, because this transpiration term, if it's measured with eddy covariance, also includes evaporation from soil and other surfaces, that means that GC also includes a conductance due to those evaporation terms. So it's a little bit more complex of a term. That being said, very often that GC calculated from the inverted Penman-Monteith from, for instance, eddy covariance data is often interpreted roughly as a measure of the functioning, the aggregate functioning of stomata in the ecosystem, with the sort of at least implicit acknowledgement that that includes also some soil components as well. And just like at the tree level, this canopy conductance includes some architectural components because it includes not only the average stomatal conductance of leaves in the ecosystem, but also the leaf area index of the ecosystem. So it's complex, but it's also a really useful measurement of the aggregate physiological and structural function of ecosystems. So you'll see this type of approach used quite a bit in, for instance, eddy covariance and modeling analyses of transpiration from ecosystems. This final concept that I'm going to talk about is the omega decoupling coefficient. And what the omega coupling coefficient or factor does is it helps to express the relative importance of aerodynamic or boundary layer conductance and canopy conductance for controlling transpiration from a body of vegetation. As you can see, the numerator and denominator, we have these same terms here. Okay, these terms are the same. So the way this works is that when aerodynamic conductance is much, much greater than canopy conductance. So when aerodynamic or boundary layer conductance is much larger than GC, and I'll write that out, then that means omega approaches 0. Because basically as GA gets much larger than GC, that ratio gets larger. So this entire term, omega, will approach 0. Never reach 0, but it will approach 0. And then inversely then, of course, when aerodynamic resistance or boundary layer resistance is much smaller than canopy conductance, that makes this ratio here approach 0, which means omega approaches 1. Okay, so omega varies from 0 to 1. It's an index. And at those two different extremes, it expresses the two extremes of relative control of boundary layer term. So basically that boundary layer resistance caused by laminar air versus canopy conductance, which is roughly stomatal conductance control, and the interaction between those two, or the relative control of those two. So here's some examples of omega sort of on average for a number of different forests and crops. So what you can see here is, for instance, for these forests, these are situations where omega is close to 0. These are situations with very large aerodynamic conductance. So the boundary layer resistance is not a factor here. These are tall, rough forests, which means the boundary layer conductance is large, or the boundary layer resistance is very small. It's not important. Conversely, these are situations with trees, especially conifers, where canopy conductance, which we can roughly think of as stomatal conductance, is relatively small. So between those two, what that ends up meaning is that this term, the canopy conductance term, has the greater control over transpiration. In contrast, these field crops, they're short and much more densely packed, so they have smaller aerodynamic conductance or larger boundary layer resistance, and they have relatively large canopy conductance, so their stomatal conductance is high. Those two things together then end up being a situation with omega approaching 1, where boundary layer conductance ends up having a greater control over transpiration. And then some of these intermediate values, some of these are intermediate, where there's relatively more even balance between the relative control due to boundary layer and stomatal or canopy conductance terms for controlling transpiration. In general, conifers are usually assumed to have relatively small values of omega, where then stomatal terms are really important for controlling transpiration, but that can vary. Here's an example where omega can actually vary through time. This is in Pacific silver fir, a conifer canopy, and normally, again, we would expect conifers, because they have relatively low stomatal conductance and relatively high boundary layer conductance, we'd expect them to have relatively low values for omega. And in general, you can see on these 2 days that we measured, they do. These are hourly values over 2 different days, calculations of omega. But you can see during a few periods, omega actually gets relatively high for this conifer canopy. And that is periods of time, basically, when wind speed is low. So during really still periods of time, remember, boundary layers tend to build up during periods when wind speed are low. That shows us that during those periods, actually, omega may rise even in conifer canopies, because that boundary layer, this shows the time series of boundary layer and canopy conductance for that Pacific silver fir canopy. You can see that during those periods of low wind speed, that aerodynamic conductance is actually quite low. So during those periods of time, those are periods when actually that low aerodynamic or boundary layer conductance ends up being a limiting factor for transpiration. The other way to think about it, looking at the next slide, is that we have 2 different extremes where either radiation or vapor pressure deficit more strongly control transpiration. So in these cases, this is essentially transpiration. Their notation is this is the transpiration imposed. This is the situation where omega is near 0. Another way to think about this is that boundary layer conductance is much, much larger than canopy conductance in this situation. So when boundary layer conductance is very large, it essentially means it's not a factor. And when boundary layer conductance is not a factor, that means GC is then the primary factor controlling. And if you basically take boundary layer conductance to infinity in the Penman-Monteith equation, you end up getting this formulation. So this is the Penman-Monteith equation when aerodynamic conductance is infinite. When we do that, some terms cancel out, and you can basically see under those conditions that really the only terms that are important, these are all constants. The only terms that are important are canopy conductance and vapor pressure deficit. Those are the 2 controllers of transpiration. This is the opposite situation. So in this case, we've taken, this is the situation when GC is much, much larger than GA, or another way to think about it is GA is quite small. So if we take GC to infinite or make GA 0, that's what the Penman-Monteith equation looks like when you look at those types of situations. And what you can see is in those types of situations, the only factor that ends up being important in controlling transpiration is net radiation. So those demonstrate two extremes of the situation. And what omega does is couple those two situations together. So you can think about your value of omega and whether that imposed situation, which is basically control of transpiration by vapor pressure deficit and canopy conductance, is important, or whether that equilibrium situation where it's controlled by net radiation, omega expresses the relative importance of those two extremes. So essentially, this series of factors and the imposed and equilibrium formulations of the Penman-Monteith equation basically let us think about the relative importance of those different terms for controlling transpiration from stands, depending on their architecture and their physiology.